My interest in fusion got started when I was an undergraduate physics major at Boston College. I was starting to think about graduate school, and I came across a book called Project Sherwood by Amasa Bishop, who was at the Atomic Energy Commission at the time. And it described a field of research that was just being declassified. It had been carried out in secret for like 10 years by the U.S. and other countries. And it seemed to me like it was a very exciting field, a new field, a field of physics that would also make a difference in society if it paid off. And so for all those reasons, the fact that I could get in at sort of an early phase of the field and spend a career working in it, for all those reasons, when I started looking for a graduate school, I went to a school that could teach me about fusion. The thing that really interested me about fusion was the fact that the fuel came from water as opposed to having to burn coal or find oil or gas and things of that sort. And it seemed to me that also it was a nuclear source. At the time I was getting into fusion, Admiral Rickover had just put the first nuclear submarine out to sea. And it seemed to me that nuclear was a very important field of physics. And it also seemed to me that fusion was a little bit better than the conventional fission of that was nuclear physics was based on. So for those reasons, it seemed to me that fusion was something that on the one hand was a very long-term, very viable energy source, but on the other hand was more safe and than the other forms of nuclear power. In the early days of fusion research, people were very optimistic that it could be developed very quickly. I think that was because after the atomic bomb, the hydrogen bomb was developed very quickly. And then very quickly after that, we had nuclear power. And Admiral Rickover, for example, when he decided to build the first nuclear submarine, from the time he thought of doing that till the time he went to sea was like 3 or 4 years. And so scientists were generally very optimistic that things could be done quickly. I think during the 1950s, as they were doing all this secret research around the world, they realized that there was a lot about fusion that they didn't understand. Even at the very first conference on fusion in 1958, where everything was declassified around the world, predictions were made that we would have everything finished in 20 years. That was already a longer time than people had originally thought this would take. As time went on, the 20 years kept becoming another 20 years, and the reasons for that are multiple-fold. Partly it was the difficulties that were encountered. As people did experiments, they thought they would find something particular, they would find something different. And they would have to then go back and understand that, develop new theories, and then go out and test these theories. And all this took a lot of time, and a lot of different things were tried. And so as we went along, the time scales kept changing a little bit because the difficulties became more and more understood. But as things settled down, people realized that in order to get from the kind of experiments that we had in the laboratories to actually a power-producing plant required major investments in construction of large facilities. And this created a problem of how much were these facilities going to cost and how long would it take to build them. And as time went on, every time we were sort of ready to build a new large facility that would accomplish another major step towards the goal, one would run into a problem very frequently that turned out to be exactly the time that the government was trying to reduce funding for everything. And so we had problems for the last 30, 40 years that the money that was required to take these steps to build on what we just learned was rarely available in order to take those next steps. So for example, today, the major facilities that we have in the U.S. were facilities that we actually invested in building back in the 1970s. So these are really old facilities. They've been upgraded many times. They're still productive, but we never took the next step beyond those facilities that would allow us to sort of cut another 10 or 20 years off the development schedule. Well, fusion's been going on for a long time. It actually started back in the 1950s, and progress was relatively slow for the next 10, 20 years. But during all that time, understanding was being developed. And confinement of the fusion fuel was the major issue. And another major issue was raising its temperature to a temperature that existed like in the sun. So people tried a variety of different ways to heat this gas. And over the years, we have already achieved temperatures, greater than are in the sun. So the first major stumbling block, if you will, of heating this gas to a very high temperature was achieved quite a while ago. Back in the 70s, for example, we achieved what we call the ideal ignition temperature for a fusion fuel at Princeton in 1976. We did this. And then we built a machine that would do even better. And then on the confinement side, many of the experiments showed what we called anomalous losses. The plasma was getting out of the vessels faster than the theory predicted. And we tried a variety of different types of what we call magnetic bottles to do this. And then the Russians in like 1969 came through with a breakthrough. They had created a magnetic bottle or a magnetic configuration that did like 10 times better confinement of the gas than any other experiment in the world and any other configuration. And so that in the 70s created sort of what a bandwagon effect of all the countries started building these things called tokamaks. And so as these different things came to pass where people would learn these things, stepping stones were made and the confinement improved and improved. And so now we're right at a point now, as a result of all this progress, that we're actually building over in France as an international project a facility that can actually make 500 megawatts of fusion power. So we've gone from little experiments where we had low temperatures and poor confinement to now we are building a real first fusion reactor. In making progress on fusion, there are two types of topics that you need to address. One is the development of understanding in experiments, and then putting that to work to build a better experiment. And this is a technical thing in terms of when are you ready to know enough in order to go out and build, for example, a power plant, which is the end goal. That costs money. So in addition to technical understanding, the other question about fusion schedule and timeline is the flow of money. Now there's two types of money. There's ongoing money for people and doing small scale experiments. And then every now and then you have to have a large influx of money to build a large new facility, because the kind of experiments you have in the laboratory do not make electricity. And the kind of projects that make electricity are very expensive compared to your laboratory experiments. And so in order to get from where we are today, which is a scientific research program, to an electric utility power plant, you have to have periodically construction projects which cost a lot of money. And so if you never get that money for construction, you can never get to the power plant. So we laid out a plan in 1976 that showed a series of facilities that were needed. The experiments that we had, a bigger experiment after that, and then a power plant. Each one took a certain amount of time to build, and each one cost a certain amount of money. And so we laid out a plan that says, okay, here's how you do it. You start from where you are today. If you take a series of steps in terms of building facilities, you need a bump in funding to build one, and then you operate that, then you need another bump of funding to build the next one, and then you have another bump of funding to build a demonstration power plant. But if you never get those bumps in fundings to build those facilities, in other words, if you never get agreements to construct those facilities, but you still keep the program going, so you have the money that you always had, and you just spend that forever, but you never get these construction projects, then you'll never get there, because you have to have these construction projects and these facilities in order to demonstrate that you can do the engineering, that you can do the testing of reliability of components, and that you can actually make power for not just a few seconds, but all day. And so each of these things costs money, and if you don't get that money, but you still get money for research, you'll never get to the power plant itself. You'll have a good program, you'll learn a lot. Someday you'll still have to get that money for these facilities in order to get there. And if you don't get that money, the time just keeps drifting out into the future. And we showed that in 1976 plan. We never got that money. Recently, people have gone back and looked, from year 2012 back, and showed that we actually, if you look at the history of the budget, we never got that money for those construction projects. As I mentioned, we're still operating in the United States facilities that we got money for in the 1970s. After that, we never got the money in the 80s or 90s or the 2000s to build these major new facilities that you needed as prototypes before you could actually go out and build a power plant. So fusion's been going on for a long time. We haven't been getting the money we needed in order to build the facilities that we needed. The question is, starting now from what we've learned over the past 50 years, what do we need in order to get to where we want to go, which is an operating electricity producing power plant? The Department of Energy over these decades has periodically carried out major reviews and from advisory committees to answer this question. And they've all said the same thing, namely, you have a great research program, but in order to get to a power plant, you have to bring in engineering groups, not just physics groups. You have to bring in industry and not just universities and laboratories in order to develop an industry out there that can produce an electric power plant to sell to utilities. So in order to get from where we are today, which is a very good research program, a lot of good physics understanding, to a power plant, we need to add to the program that we have today a very significant engineering development component to the program. We have to bring in industries to develop these components, to test them, to show how they fit together, to show that they're reliable, to demonstrate how you would maintain these power plants in order to determine what the costs of the power plant is going to be. Because if you just develop something that's so expensive that someone would say to themselves, well, that's a very nice power plant, but it costs 10 times more than the coal plant that I could buy. So we have cost issues in fusion that have to be studied, and these kinds of issues about costs of facilities and power plants, these are best addressed by industry, by engineers, and not by physicists, because physicists develop nice physics experiments. They don't cost that much. They don't care if they break down every week, because they just fix them and do them more physics the next week. But when you get to a power plant, you have to have it reliably operating every day in a cost-effective manner. And the kind of people that do that kind of work, that kind of development, are engineers and industry. And right now, and for many decades now, the government has only been willing to fund the physics research. And so to answer the question that's often asked, what do we need that we don't have? We have great physics. We don't have the engineering that we need. We don't have the industrial participation in the U.S. fusion program that we need in order to become a commercial success. I think a lot of people in the lay public do not even know what fusion is. Let me tell you why I think fusion's important and why I think I got into it when I first learned about it. The thing about fusion is, for example, that the energy that you can get out by combining two hydrogen atoms, namely fusing two hydrogen atoms, it makes a helium atom. Einstein had this formula that energy equals mass times the velocity of light squared, that you can convert mass into energy. So what happens is when you put two hydrogen atoms together to make helium, some mass disappears, and it appears as a great burst of kinetic energy of the particles. And it turns out that the amount of energy that produces per pound is a million times more than the energy that's produced from burning the same amount of coal in terms of mass. And even compared to nuclear fission, which is the splitting of uranium, that also is a nuclear process that makes energy, fusion per pound gives out 8 times more energy per pound of mass converted than fission. So fusion is probably the most energy intense for a small amount of fuel that you can get. It takes, for example, to run a power plant, say 10,000 carloads of coal in a year to run one of these power plants. You get the same amount of energy from that power plant in a year. How much fusion fuel do you need? You need a half-ton pickup truck worth of hydrogen fuel. So a small truckload of fuel goes into the plant, it runs the whole year in fusion. But for a coal plant, 10,000 carloads of coal, they all have to come in, they burn the ash, they all have to come out, be disposed of. So fusion is an ideal energy source from that point of view. But the process itself is very simple. You get hydrogen from water, you take these hydrogen atoms, you heat them to a very high temperature like exists in the sun. When that happens, these fusion atoms combine by banging into each other and they form helium, and the mass disappears in the process, in the nuclear conversion process, and you get way more energy for a very small amount of mass compared to any other energy fuel source that you can think of. Oh, except for solar and wind, of course. This year is my 50th anniversary of being in fusion. I started in 1962. I've done research in fusion, I've been in the management roles in the government, and I've been in this nonprofit foundation for a long time. So I've been tracking fusion progress and been involved in lots of conferences and things for a long time. And it occurred to me a few years ago that no one is putting all this story together about what the history of the fusion program is. I got interested in fusion because of a history book that was written that only spanned 10 years of the first 10 years of fusion. Since then, there was a book that talked about the history of fusion up to like 1982. So that was 20, 30 years ago. So I decided a few years ago that I would write a book on the history of fusion. My book is called Search for the Ultimate Energy Source, a history of the U.S. fusion program. And it tracks not the detailed technical accomplishments of the program, although those are in the book, but primarily the political ups and downs, the budgetary ups and downs, the management ups and downs, the changes of policy from one president to another, from one agency to another. We've gone through Atomic Energy Commission and became the Energy Research and Development Administration. Now it's the Department of Energy. Every time these changes happen, something happens in the fusion program in terms of momentum, in terms of policy, and in terms of budget. And I thought someone ought to lay all this out and track it through time as a contribution to the history of the program. So it's sort of a legacy, if you will, of my perspective in my career in terms of that aspect of the fusion program. And I hope it makes a contribution to the literature, if you will. I don't expect it to be a New York Times bestseller. I hope it will give new people coming into the program a perspective on the program and how they fit in, and what they may be up against during their career in terms of not being able to accomplish the things that they want to because they can't get the money for it or whatever. So that was my intention, and my book should be coming out next year in 2013. In the 1970s, I was a manager of the fusion program at the Department of Energy, and a congressman named Mike McCormick, he decided that he would put a bill together, which he did with Senator Paul Tsongas in the Senate, and they passed this bill, and Jimmy Carter signed this bill. It was called the Magnetic Fusion Energy Engineering Act of 1980, and it said, let's have fusion by the year 2000. I was at the department at the time, and it built on the plan that I had written in 1976 that had these different budget profiles in it. And so I decided that in order to implement that kind of a program, to have fusion by the year 2000, we needed to bring in industry. So I decided, I contacted a bunch of people in the industry, and with support from 10 industries, we formed an organization called Fusion Power Associates, which I am still president of today. Myself and 2 other people, we incorporated this as a nonprofit foundation. Its purpose was to bring industry into the fusion development program to do the engineering and development that would allow fusion to become a practical energy source. And for about a couple of years, that looked like that could be done. But when we didn't get the money for the first fusion engineering test reactor during the 80s, the character of my organization started to change. Because electric utilities, for example, that were going to be our customer, they got deregulated. They started thinking about, they were taken over by budget people who were thinking about near-term profits rather than long-term energy sources. And so a lot of things happened during the last couple of decades to my organization, where our original purpose was to bring in industry to do engineering development, and we had to evolve as the policies evolved so that we started to become more interested in the research. We brought in more of the laboratories and universities into our organization. We started to lose some of our industries, and we've become a more, what do you say, go with the flow, if you will, of government policy to try to keep the hope alive that someday we'll get to fusion. So we run a lot of conferences. We try to keep all the different parts of the fusion community, if you will, talking to each other. They don't always talk to each other. There's a lot of competition between different people with different ideas. I try to keep them all talking to each other by running these management level conferences, by putting out newsletters in which I advertise all their different kinds of results so that they see a little bit about what each other's doing, because there are a lot of specialized areas in fusion, and people tend to work, especially physicists, they work in their own little areas, and they don't think about the big picture very much anymore. So for those reasons, Fusion Power Associates has become kind of a melting pot, if you will, for all the different constituencies in fusion. But we've never let go of the other element of our goal, which is, in order to have fusion supported by government, we have to have a certain amount of congressional support, an understanding, and a certain amount of public support. And so we try to make sure that we participate in that educational function also. Well, there is one thing that I would really like to emphasize. Fusion is an energy source, but it is not the only energy source. We have a problem with energy in the future. The population of the world is growing. All of these people that are in developing countries need energy, and this is going to create great demand. Most of our energy today comes from burning of fossil fuels. Many people in the world, especially the scientific community, believe that continuing to burn these fossil fuels is going to create global warming and damage our life in the planet as a whole. And so we're going to need new energy sources. We're going to need a lot of energy sources. We're not going to have just one energy source. Fusion is not going to be the only energy source. We're going to need every energy source that we can get. We're going to need to develop wind. We're going to need to develop solar energy. We're going to develop nuclear energy, and we're going to need to develop fusion. And so we have to take the long view. These things take time. New energy sources do not come into play overnight. They enter the marketplace slowly with time, and we have to understand that time is, in a sense, running out, not maybe on a 5-10-year scale, but on a 50-100-year time scale. We have a real energy problem, and we need to develop every energy source we can get. And one of the very great benefits of fusion is that it's not just a small-scale energy source that's going to make a small difference. It's a huge energy source. The fusion power plants are large. They make lots of power from a very small amount of fuel, and so they are going to be what we call base load. They are going to provide not just small niches here and there for this or that out in the deserts or wherever in the mountains. They're going to be running our cities for electricity and for other things. Fusion can make not just electricity, but it can make other things. It can do, for example, desalination of water. Water is going to be a big problem on the planet as time goes on. So there's many reasons to develop fusion, but it's not the only energy source, although I think in the long run it is going to be one of the most important energy sources. Not next year, not in 10 years, but in the 20, 30, 50, 100-year time scale, fusion is going to be essential for the planet.